Hello, my name is Mocinaldo Medeiros. I am a computer engineer and researcher at the Federal University of Rio Grande do Norte, Brazil. Today, I'm going to present my work named Multi-Layered Methodology for Driver Behavior Analysis using Tiny Machine Learning and Edge Computing. Here is a brief summary of what will be presented. We'll start by contextualizing the area where this work is located, moving on to the proposed approach, the hardware used, the case study carried out to validate the proposed approach, the results of this experiment, the conclusions, and the future works. The context of this work lies mainly in the application of tiny machine learning, or TinyML for short, and edge computing within the contemporary automotive sector, which has been influenced by the proliferation of sensors integrated into vehicles. To collect the data produced by these sensors, the OBD-II protocol is used through two approaches. The first using Bluetooth devices connected to smartphones, and the second using a device based on Internet of Things concepts that performs the processing and sending of data to the cloud independently from a smartphone. These devices are known as OBD-II Edge and have microcontrollers that allows the creation of soft sensors for local processing of data from physical sensors. So the idea here is to use this second approach to classify driver behavior by running real-time TinyML models at the edge of the network and using low-cost and low-power hardware. Therefore, the proposed approach has as input the continuous flow from data from the vehicle's sensors that initially enters in the first layer, which performs the calculation of a soft sensor, that is, a sensor that is not physically in the vehicle. In this work, engine load, speed, RPM, and throttle position sensors were used to calculate the total area of a radar graph. This graph represents the amount of vehicles resources that were used. The values from this new sensor are then continuously pasted to layer 2, which uses an algorithm called TEDA to detect and eliminate outliers. To do this, it uses concepts of typicality and eccentricity of the data that previously passed through the flow. Proceeding to layer 3, the incremental clustering algorithm takes two inputs, the filtered data coming from layer 2 and another selected physical sensor to perform the clustering. After a correlation analysis of the sensors, the engine load was chosen as the second input of this layer. To carry out the classification, three drivers profiles were defined based on the literature: cautious, normal, and aggressive. So, to represent this in the algorithm, three data clouds are defined in which the data is also grouped based on the concepts of typicality and eccentricity, the same from TEDA. This algorithm learns online, has no assumptions about the initial distribution of the data, and is capable of dealing with data drift. Once the data is grouped, this phase results in a cloud index, which represents the driver's behavior at that moment. This methodology was embedded into the OBD-II Edge Freematics One Plus, which has a microcontroller based on ESP32 with 16 megabytes of cache. Additionally, it has a Bluetooth Wi-Fi 4G module a geolocation antenna, and SD card support to store collected data locally. It is important to mention that it is open hardware and open software, so you can find both the hardware datasheet and the code in the GitHub repository. This then allows us to modify the code according to our needs, such as sending the data to a server that stores the collected and processed information. To evaluate the validity of the proposed approach, a case study was carried out with two participants, one with a 2012 round-of-fit 1.6 liters engine with manual transmission on a Wednesday between 4 and 4:30 in the afternoon, and the second used a 2014 Ford Fiesta 1.6 liters 2 with automatic transmission on a Friday between 9 and 9:30 in the morning. The route consists of approximately 7 kilometers of urban stretch in the city of Natal, Rio Grande do Norte, Brazil, familiar to both participants, and consists of turning points, pedestrian crossings, intersections, and others. Throughout the experiment, data was collected and processed every 1 second. In these images, we can see that the beginning and end of the route for both drivers were the same, with the difference that the first drove with a predominantly more aggressive and normal profile for his standards, while the second drove more cautiously. These classifications vary greatly from person to person, as one person's cautious may be another's normal, and so on. But even so, the algorithm managed to capture the profile changes that were controlled along the route. For example, in these stretches, there are speed bumps and pedestrian crossings, so there is a change and then it returns to the profile it was before. All these changes were controlled throughout the experiment, and the algorithm was able to capture them. In order to assess the stability of the proposed methodology's execution, the duration taken by each algorithm for processing and the overall execution time were computed. So this table shows the statistical distribution of these times, and it's possible to observe that the mean and standard deviation of the algorithm executions for the two drivers were very close. Furthermore, the quartiles and minimum and maximum values remained practically the same, demonstrating stability in the execution. Finally, in the conclusion, I highlight the successful use of soft sensors as a parameter of the Layer 2 and 3 algorithms. In Layer 2, there was also the successful detection and removal of outliers. In Layer 3, the driver's behavior was classified with good accuracy using incremental and online clustering algorithms. And finally, I highlight the stability of the algorithm's execution in real time. For future works, we would like to optimize the algorithm, carry out large-scale validation with more vehicles and in different scenarios, in addition to integration with a vehicle assistant as Alexa, for example. So, that's it. Thank you for your attention, and thank you very much for this opportunity to present my work here. If you want, you can send me an email and we'll talk about the work in more detail.